Okay, so today, in order to review for the exam, we're going to look at the problem out of the sample exam that I just posted, 3 or 4 minutes ago. Okay, so what about, I'll give you about 15, 20 minutes to do it, and then we do it together. So that sounds like a plan, and I just pause the recording for those 20 minutes, and then we do it together, okay? But let's just try first to look at the problem, okay? Let's see what this is about. So I've shown in the figure a hot industrial wastewater at 15 bars and 1 degree Celsius with a mass flow of 5 kilograms entered a flash chamber via a valve. So what is specific about the valve? What do you know about the valve? Is that through the valve, the enthalpy will remain constant. Okay? That's what you need to remember about the valve. Saturated vapor and saturated liquid streams, each at 4 bar, exit the flash chamber. So they are saturated vapor on this side, saturated liquid on this side, but the pressure is the same. So this is a constant pressure, no? Yeah? Okay. And remember, the enthalpy here is the same as the enthalpy here. So that should help. Right? The saturated vapor enters the turbine and expands. So now the saturated vapor enters the turbine over here and expands to 0.08 bar and 90% of steam. Okay. Straight heat transfer and kinetic and potential energy effects are negligible. So basically Q equal to 0, change in kinetic and potential energy will be equal to 0. For operation at steady state, determine the power in horsepower developed by the turbine. So you need to find how much power you need to give for the turbine for this to happen. Okay? Alright, so it's 9:48. I'll give you, let's say, until what? 10:05 or 10:10? Okay. Pause it and then we do it together. There we go. Okay, so this is basically the graphic that I've done for this problem, and basically the substance we are dealing here is water, no? Because they talk about saturated vapor and saturated steam. So what we need to find is the power in the turbine. Okay, so the first thing I will do is that. Okay, so what should be our control volume? So let's say I select this one as our control volume here. All right, and then we see what is the data that we need to find in order. Let me hide the mouse. Okay, so for this control volume, what do we have? The equation is Q dot minus work dot plus M. What we have? M2 H2, no? Is coming in, correct? And that will be equal to, okay, and M4 H4, no? But you agree that here, because of the conservation of mass, M2 and M4 should be equal. Okay? So what would that mean? So we know there is no heat transfer. This is 0. So we could say that the power of the turbine here would be equal to what? H4 minus H3. Wait, H2, no? What did I say here? H will be equal, sorry, to will be equal to H2. I was looking at the figure, but I was thinking about something different. Will be equal to H2 minus H4.
How do you know that Q is equal to 0?
Because they say that it was not. I'm just saying that this part looks too easy for now. So let's see. What was the problem statement? I thought I had it on. Remember what it was?
It's in one of your Adobe things, I think.
Adobe?
Yeah.
No, that's a solution. I think it was on the here. He says that the saturated into the turbine, straight heat transfer and kinetic and potential energy effect are negligible.
I see.
Okay?
Thank you.
But when I do this, it looks like we don't even need M2 or M4. Yes?
So in that last equation that you had written,
Yeah, I think it's, I might have done.
why is the mass flow rate not a part of that somewhere?
That's what I'm saying, because what happened is that, we need we need to find the mass flow. They are equal, but we need to find it, okay? That's exactly what I was saying. Sorry for that. I was trying to think ahead. So this will be equal to this, sorry for that, and then we have this will be M2, no? Because M4 equal M2, so this one would be H2 minus H4. All right. I was trying to think ahead. Sorry for that, guys. I was trying to. Okay. So this is really the equation we need to solve. So out of this equation, let's see what we can find quick. Can we find, let's say, H2 pretty quick? What do we know? Do we know two things about point 2? We know it's saturated vapor. And we also know that P2 is equal to 4 bar, no? Okay? So from here, we could go to the tables. So this is the temperature, so it would be table A2, no, table A3 at 4 bars. We need to look at saturated vapor, we need to look at H sub G, no? Yeah? So which is 2,738.6. So we find table A4, H2 equal to Hg for gas, equal to 2,738.6. Okay, that's what I have over here. All right, now, do we know two things about point 4? Yeah, we know H4. What is the state? Since they give you the quality factor, you know it's going to be a mixture. Okay, and you know it's at P4 equal to 0.08. So that means that H4 is going to be equal to H fluid plus X4 H gas minus H fluid, which now we can get the data from the table. So table A4 is 0.08. Okay, we can copy this value. So table A4 we find that H fluid is 173.88 and H gas is 2,577. So if we substitute into that equation, what are we going to get? All right, so that H4 will be equal to 1073.88 plus 0.9 times 2577 minus 173.88. Which gives you what for H4? Okay, maybe we can do the calculation. But I think I also have the solutions here, so we can double check. Let's see, they have H4. H4, they don't have it. Equation 1. Okay, so it did the same thing as we did. So what is H4? So it's H4 2336.69. Is that what you get? Looks about right. No?
That's what I did.
So 233.36.69. Okay, that way we save some time on the calculation. All right, so that's what we get. All right, so we got H2 out of this equation, we got H4. Now we need to find M2, no? Okay? So we need to find M2. So let's see, in order to find M2, this time what can we do? So this was our control volume, let's say control volume 1. Control volume 1. And now we need to determine a second control volume. So let's say our second control volume will be this chamber over here. Okay? This one over here. So for control volume 2, and this is important that you let me know for which control volume, okay? So for this control volume, we're gonna have again Q dot minus work plus what is coming in? M dot 1 H1. And now what is coming out will be N dot 2 H2 plus N dot 3 H3. Okay? So now, from here, we know, is there any work or any Q in this control volume? No. So we can say that this term will be 0, this term will be 0. Okay? And at the end, we're going to have here that M2 will be equal to what? So M dot 1 H1 minus M3 H3 divided by H2. Okay, but over here, we only know, maybe I should not read in this because the equation will become more complicated. Maybe, okay, look, scratch this equation. I think it's just going to make it more complicated. All right? And now, what I'm going to say is what? What do we know about M3? And using mass conservation, what does that mean? M dot 1, the quantity of mass coming in, needs to be equal to the amount of mass coming out, no? So it should be equal to M dot 2 plus M dot 3. Okay? Or I could just write here, M dot 3 will be equal to M dot 1 minus M dot 2. So now if I combine these two equations, What do we get? M dot 2 H2. Oops, I forgot the M dot 1 H1 equal to M dot 2 H2 plus M dot 1 minus N dot 2 H3. Okay? So if I do some minor algebra, it would be M1, M dot H1 will be equal to M dot H2 plus M dot H3 minus M dot H3. And this is going to give me M dot 1 H1 minus M dot 1 H3 will be equal to M dot H2 minus M dot 2 H3 or what happens over here, that M dot 2 will be equal to what? M dot 1 H1 minus H3 divided by H2 minus H3. Any questions so far? Okay, so basically out of this equation, what do we know? We already know H2 that we found before to be equal to 2,738.6. But we need to find H1 and H3, no? Okay, so what do we know about H1 and H3? All right, do we know two things about H1? We know the pressure and the temperature, no? So let's go H1. What will be the state of H1? So H1 is 15 bars. So 15 bars is 198. Okay, so what is the state? We know the state would be, how much is 180? It would be liquid, no? Okay, so if it's liquid, be careful here. What you need to do is you need to go to the table of the temperatures and see what would be from table A2, the H at 180. Okay, so at 180, what would be the H? H fluid is what? 700 and, I'm on the red line, 763.22. All right, so H1, we go to, so state is liquid because T is lower than T saturation. So we go to table A2, H1 equal to H fluid equal to 763.22. All right, so that's what I got over here. So we know H2, we know H1. We need to find H3. Okay, do we know two things about H3? We know the pressure and the state. So we know P3 equal to 4 will be saturated liquid So now we can go what? To table A3. H3 will be equal to H fluid again. And what would that be? Table A3 at 4, H fluid 604.74. Okay, let me see here. They have those values here. They give the value for M2. Okay, so we should find 0.371. Let's see if we find that. So over here, now we substitute into the above equation. So substituting into M2 equation, what do we get? M2 is going to be equal to M1, which is what? 5 kilograms per second. So it should be 5. Now H1 we found to be equal to 763.22 minus H3 604.74 divided by H2 2738.6 minus H3, which is 604.74. And this gives you M2 to be equal to what? Is it about 0.371? Yes? Okay, 0.371. Kilogram per second. So now that we have M2, what can we do? We can go back to this equation, to the star equation, all right, and substitute for the final values, no? So finally, from equation star, which is what? The power of the turbine is equal to M2 H2 minus H4. Be careful here with the units. So we have M2 will be equal to 0.371 kilograms per second times H2 2738.6 minus H4. H4, what we found before, H4 to be equal to 2336.69. 336.69. Now this is what as unit, this should be what? This should be kilojoules per kilogram? No? But they're asking us in this problem to find the answer in horsepower. So if you have that page that I give you with the units, you have the transformation of kilojoules to horsepower, which I don't know which one it is.
It's 0.7457.
So what is it? The 1 horsepower is what?
0.7457.
0.7417? 57 kilojoules per kilogram?
Kilowatts.
Kilowatts, yeah, this is a kilowatt.
Yep.
Okay, kilowatts, yeah. Correct, because a kilojoules per second is a kilowatt. Okay? So you do this unit transformation, do the calculation, but I'm going to go and check. If we didn't do anything wrong, this should give you about 200 horsepower, 199.9. Okay? Is that what you get? Go and check, please. And you have the same numbers? Okay, but again, I mean, I look at the solution so we can go a little bit faster, no? But so this should give you that the power is 199.9 horsepower, which is a lot. I mean, it's not a lot, but okay. So this was page 91 and 92. All right, let's see if we have time for another problem. Or at least you can do it, and then we can do it very quick. I just go through the procedure. Okay, I'll let you do the fill. So where are the problems here? Here we go. Here was problem 1. Which one you want to do?
Which one's harder?
I don't know.
Let's do number 2.
Let's do number 2, okay? So read this problem. I'm going to put now this on pause again. And I'll give you about 10-15 minutes to do it, and then I'll just go through the procedure, okay? All right, so let's see over here. So this is the important part, the figure. Once you get the figure. Now, what type of problem is this? This is an open system or closed system? Closed system, so the mass is constant, no? Okay? There is no mass flows. All right, so over here, let's see what happens. So what do we know about state 1? We know it's 1 megapascals and the temperature is 500. So you can either go to table, whatever, A3, but I mean, let's go to table A3 if you want, which would be the normal. So here they give the pressure in bars. So 1 megapascal is basically 10 bars. Okay, so at 10 bars, what is the temperature? 179.9. So what does that mean about the state? Is that going to be superheated? No? Okay, so we can go now to these tables here, which is already in, you see the 1 megapascal over here is 10 bar, the temperature is the same, 179.91. All right? Okay, so that means that if we are on this figure over here, if we are here at P1, equals 10 bar, point 1 is going to be somewhere along this line here. Maybe along this line here. This is going to come from one of those temperature lines of 500, because what is the line over here? The line for 10 is 179.91, no? Yeah? So this should be coming from a temperature which from a much higher pressure, no? Okay? But it doesn't matter. The fact is that we know it's superheated. Now, what else do we know? So we know, okay, so from table A4 at P1 equals 10 bars and T1 equals 500 degrees Celsius. What can we get from that table? So let's see. So from that table as 10 bars and 500, let's say that we're going to get the volume, which would be 0.3541. So V1, specific volume V1 would be 0.3541. And now, when we are dealing with closed system, do we need to talk about H or U? We talk about U, no? Yeah? So U will be 3,124.4. Okay, I'm going a bit faster here just to get the data already. So, all right, so over here, this will be here V1, no? What do we know about state 2? Or after the second process, process 2. We know that V2 is half of the initial volume, no? That's what they give us. So that will be equal to what? 0. So can you do a calculation for me? 0.3541 divided by 2 will be 0. What? 175.
17705.
17705. 7705. Okay, and this should be cubic meters per kilogram. Okay, so what else do we know at 2? We also know the temperature. And we know, so now we know two things, and the temperature T2 is 25 degrees Celsius. Okay. So process 1-2 is constant pressure. So let's see at 10 over here, table A from table A3. Table A3. Are you following me here, or am I going too fast? What I'm trying to find is, out of this figure here, what is the value of V gas for 10 bars, no? That way we know if we're still on this area, or we are on the mixer, or we might be even on the liquid, no? Depending on the value of the V. So let's see what the value of V is. So at 10, you can find what's on top. Let's see what V gas is. 0.1944, okay, and this will be 1.1273 10 to the minus 3. So that means that we are in the mixer area, correct? Yeah, so that means that we go from 1 over here, it would be 1 to 2, somewhere over here. And we know that V2 is equal to 0.17705. Okay, so since we are on the mixture area, we need to find what is the quality factor. So the quality factor meaning that we need to find what is X2. Okay? So if we know, so what should be the quality factor? What? So from table A3, I'm guessing at P equals 10 bars, we get V gas, V fluid equal to what? So V gas, V fluid at 10 is, so V gas is 0.1944 and V fluid is 1.1273 10 to the minus 3. Let me go to the next page, which I have. Okay, this is my last page over here. I think I have another block. All right, so from here, what do we know? We know that V2 should be equal to what? V fluid plus X2 V gas minus V fluid. So from this equation, we can find that the quality factor of 2X2 is V2 minus V fluid divided by V gas minus V fluid. So we substitute the data. This will give you what? 0.17705 minus 1.1273 10 to the minus 3 divided by V gas, which is 0.1944 minus 1.1273 10 to the minus 3. And if you want, you can do a bit of cheating to go a bit faster. Let's see what it did over here. 0.91, is that what you get? Okay, that's what I get over here as well. So 0.91. All right. 0.91. Okay, similarly, what we need to do, since we are doing this now, from table A3, at P equals 10 bars, we need to find UG and U fluid. So we can calculate U2 will be equal to U fluid plus X2 U gas minus U fluid. Okay? So at 10 bars, we're gonna have that U, well, right here, U fluid would be 761.68. And that U gas, oh wait, yes, 761.28, 2,583.6. And if we substitute into this equation here, we found what would be the value of U2. And U2, since I'm going to do some cheating here, I will look at the solution, will be what? I guess it's this one, 2,419.63. Got one check. All right. Okay, so we can do at least half of the problem over here. Let's do it now. So we know that process 1,2 from the figure is a constant pressure process, no? Yeah? So process 1,2 is constant pressure, so that P1 equal P2. So in that case, what was the definition? The work is equal to what? Integral of P dV, no? Did they give us the mass in this problem? Yes. So this should be equal to what? A constant mass, it should give M P V2 yes, V2 minus V1. Do I need to elaborate this equation, or that's fine? I mean, this one should be fine, no? Yes or no? I mean, is it good? All right. So from this equation, what do we get? Work 1,2 will be equal to what? I think the mass is 0.1 kilograms. The pressure is 1 megapascals. So the one that will be 1 times 10 to the 6 pascals times V2 that we found to be equal to what? 0.17705 minus 0.3541. So if you do this calculation, you should get, let's see, work 1, 2. Do you get negative 17.71 kilojoules? You should get a negative value, so negative 17.71 kilojoules. Okay, I won't be able to finish the whole plan, but at least we're going to finish the first part. The second part is a lot easier. Process 1, 2. Now, what can you do? You can apply the first principle of thermodynamics, and we say what? Q12 minus work 12 will be equal to what? M U2 minus U1. So you can write here that Q12 will be equal to M U2 minus U1 plus work 12. And if we substitute for the values, which I'm going to cheat and look at it, this should give you minus 88.19 kilojoules. Okay, so now maybe let's look at the solution. That way you have it. We don't have time to finish it. But now, just by looking at the figure, what should be the work between 2 and 3? This is a constant volume. Remember, the work is always the area under the curve. When it's constant volume, the work is 0. Okay? So the work between 2 to 3 will be 0. So now you can apply again. The first principle of thermodynamics will be Q minus work will be equal to M U3 minus U2. Okay? We know U2, we know the work will be 0, but we need to find 3. At 3, what do we know? Again, we know this is a constant volume. We need to go to table A3 and see what happens at 25, no? What was the volume? And so basically we'll be here at 25. You find that it's also a mixture. You can find from the figure. If this is constant, 3 needs to be a mixture, no? You cannot go outside the curve. You need to go to this curve at 25 degrees. All right? Okay? You need to calculate the new x3 by finding this value and this value. You know V3. V3 will be equal to V2. Yeah? From this curve at 25, we should be table A2. Table A2 at 25. You know the values for VG and VF, no? You do as before in order to find X3. Okay, this will be on the video. X3 will be equal to 0.0041. Okay? Once you know that, you can do the same thing to find U3. And then Q3 should be equal to what? M times U3 minus U2. And you find whatever is over here, minus 230.52. Okay? You have the solution on the video, no? So you can look at it if you want. All right, so let's stop over here. So any question about the exam?